Hello everyone, today we're moving beyond conventional academic cases to explore the strategic complexities of a continuous space location problems. Unlike discrete models we analyzed previously, continuous models determine the optimal coordinates of a facility on a two-dimensional plane without being restricted to predefined list of candidates. In the field of industrial engineering, we recognize that while these models are useful for their mathematical simplicity, they present a unique challenge. The optimal coordinate might fall into an infeasible area, such as a body of a water or a restricted zone. However, as engineers, we utilize this result as a primary strategic baseline to begin our engineering design process. Today we'll talk about the distance matrix, the Manhattan framework. For this analysis, we are focusing on rectilinear distance, also known as the Manhattan or city block distance. This metric is essential when movement is constrained to grid-like pattern, common in urban logistics and internal plant layouts. And for mathematical expression for the distance between a new facility X and existing facility Pi is defined as the sum of the absolute differences of their coordinates. And as you can see, our set is parameters variables, so we'll continue there. Our objective is in some location problem where we aim to minimize the total weighted transportation cost across the entire network. This ensures that our facility is positioned to provide the highest service at the lowest operational expense. And so we can continue our mathematical problem in GAMS. So we define our variables Ri and Si. And we sum up Ri and Si, and this allows us to maintain a purely linear objective function while ensuring non-negativity for our variables. And for the equations, notice the structure of the x and y equations in the code. By using the auxiliary pairs, the solver can identify the global optimum with the computational instability of nonlinear gradients. This reflects the equivalent linear model approach, which is the gold standard for the rectilinear single facility problems. So today's case study is analyzing the optimum, global optimum. Let's examine the results of our Turkey logistics network, where we evaluate it for major industrial hubs from Istanbul, Bursa, Ankara, and Adana. And our results, the model established the optimal coordinates as 11 and 2. And we can ask, why did the solver choose these coordinates? This aligns perfectly with the median method logic discussed in our technical documents. Since Adana is the man's weight is 12, which is nearly half of the total weight of 31. The optimal y-coordinate was heavily pulled toward Adana's position, and when a single facility is weight exits or equals half of the sum of the remaining weights, the optimal location will coincide with the facility's coordinates. This is not a mathematical accident, it is a manifestation of the domain's creativity in spatial optimization. And so, as a conclusion, we can say this implementation proves that strategic facility planning is a rigorous science. By moving from the manual median method to robust equivalent linear model in GAMS, we have provided mathematical certainty for major infrastructure investment. As we have observed throughout our current academic framework, these facilities are dynamic entities. While 11 and 2 is our optimum today, we must utilize contour line methods if this location proves physically infeasible, ensuring we find the next best alternative with minimum cost penalty, and that this model serves as a resilient decision support system for a modern supply chain. And thank you for your attention. I am now open to technical questions regarding the model's logic or its linearized constraints or constraints. And you can ask me anything. And thank you for being here and see you next lesson.